Okay, kiddos, let's take a look at this problem, which is a little bit more complex than the other related rates problems. So, read the problem here. The water tank is in the shape of an inverted circular cone with base radius 3 meters and a height of 6 meters. If water is being poured into the tank at a rate of 5 cubic meters per minute, find the rate at which the water is rising when the water has a depth of 2 meters. Lots going on here. It's pretty helpful in this case to actually draw a diagram, right? This is where the steps on the right side will come in handy in IB style problems like this. So let me draw a diagram off to the right here where I've got a little bit of space. Dead space. Inverted circular cone. All right. Base radius is 3. All right. So let me label my radius here. 3. All right. And a height of 6. Okay. So this is my height. And it is currently 6 meters. Okay. Water is being poured into the tank at a rate of 5 cubic meters per minute. All right. Cubic, think to yourself, what does that indicate? Cubic indicates volume. All right. So 5 cubic meters per minute means that our dV dt is positive 5. Water is being poured into the tank, so the volume is increasing by 5 cubic meters per minute. Find the rate at which the water is rising when the water has a depth of 2 meters. Now the words here being used are a little bit different from our variables, so we want to convert them. Depth means height. So we're saying when the water has a height of 2 meters, all right? So we're given another variable here. H equals 2. All right? We know our, our radius is 3. Okay? And the height in general is 6 meters. All right, but the instant at which we want to find this rate of change is when the height is 2. All right, find the rate at which the water is rising. At which the water is rising means the rate at which the height is increasing. So we are looking for dH dt. This is where reading carefully comes into play. All right, what does it mean for the water to rise? It means our height is rising with respect to time at a certain rate. All right, so now let's find some formulas to use. All right, so we're given the volume formula. Okay, we're not given the volume formula, I'm sorry. We're given a rate of change of volume, so let's start using the volume formula. All right, and see if there's anything we need to fill in. So the volume for a circular cone, a right circular cone, is going to be 1/3 times the area of the base times the height. So 1/3 pi r squared times our height. So let's differentiate both sides of this equation because we know we're given dV dt. All right, so we are going to differentiate with respect to time both sides of this equation. And based on our previous examples, we know that since we see here 2 different variables, we're going to be using the product rule. And since one of our variables at least has an exponent on it, we're going to be using the chain rule to differentiate that one. I'm sorry, not just that there's 2 variables, but these 2 variables are being multiplied. All right. All right, and we're using the chain rule because we are taking the derivative with respect to time. Not with respect to the radius, but the derivative with respect to time. So, let's do that. What I've done here, I've pulled out the 1/3 pi because that coefficient is going to be multiplied by our derivative anyway. This just makes our calculation easier. And so, product rule, r squared is the first function, h is the second function. So we're going to take the derivative of the first function, r squared, so that's going to be 2r times the derivative of the inner function, which is r. The derivative of r with respect to time is dr dt. So that's the derivative of the first function times the original of the second, which is h, plus the original of the first function, r squared, times the derivative of the second, dh dt. All right, now let's see what variables we have, and then try to find any other missing variables. All right, so dv dt, we are good, got that. All right, dr dt, ooh, we don't have dr dt, okay. We do have r, we don't have dr dt, so I have a feeling we're gonna need that. H, our height at this moment in time, because remember, we're taking a derivative, means we're finding an instantaneous rate of change. We do have this height at this moment in time. All right, again, we do have r. This is a fixed r. And dh dt is what we're looking for. Okay, so what we need to do is find dr dt. Okay, now this is where our diagram is going to come into play a little bit. So what's happening is that water is being filled up into this cone. And so the question, what is the dr dt? Dr dt is the rate of change of the radius of the height of the water. And so we're basically saying, what is this radius expanding by as the height of the water increases, as the volume increases by 5 cubic meters per second. So this is the radius that we're trying to find dr dt for. Okay, so how are we going to find that? By the way, this is the height that we're trying to find dh dt for as well. Well, what I see is that I have a fixed radius up top. I know that I can get one variable in terms of another, all right? So if I can get one variable in terms of another, then I can basically substitute one for the other into this formula. So let's pull out this triangle here and see if we can recognize any relationships. In fact, there is a relationship between the height and the radius of the cone, right? R equals 3, H equals 6. So the relationship between the height and the radius, the ratio of H to R equals 6 to 3. That means 3H equals 6R. And therefore, well, what are we trying to find? We are trying to find R, right? So we're going to get R in terms of H, because we know H. So that means R is H over 2, 1/2 H. Ah, okay. Well then, let's substitute that in for R since we don't have it, and find the rate of change. All right, and you're probably wondering, well, what about this R? I have this R. This is not the radius at the instant that we are looking to find the rate of change. All right? So let's, in order to find dr dt, let's differentiate both sides of this equation. All right? So if H over 2 equals R, what if I differentiate with respect to time both of these? And this is actually 1/2 H, right? All right, and so we're going to see on the right side we get dr dt, the derivative of the radius, the rate of change in the radius with respect to time, the derivative of R with respect to time. That is exactly what we're looking for. And now let's differentiate the left side of this problem. Well, what is the derivative of 1/2 H with respect to time? It's 1/2 dH dt. So dr dt equals 1/2 dH dt. Fantastic. Now, we can substitute this in to there. So let's do that and find dH dt. All right, so we're going to have dH dt twice. I'm going to do this in another color. Let me just erase that line there that I just messed up entire visual line. All right, so dV dt 5 equals, actually I'm not going to do that. One-third pi, I'm just going to say pi over 3 times 2 times, oh, I also need to substitute r as well. I'm sorry, I lied. We weren't given the instantaneous r. We know that r is h over 2. Whoopsies. We have to substitute this in for this r. Okay? Times h over 2 times dr dt, which we now know is 1/2 dH dt. So, yeah, 1/2 dH dt. All right. Times h, which we know at the instant we're looking at right now is 2. All right, plus, well, again, sorry, we weren't given the radius at that instant. So the radius squared is actually going to be h over 2 squared. And h is 2. 2 over 2 squared. Oh, cool. Is 1. Let me fix up this. Our h was actually 2. All right, 2 over 2 squared times dH dt. All right, now let's simplify and solve. I'm going to pause here and then come back once I've done simplifying and solving. Okay, so we get the dH dt equals 5 over pi, which is approximately 1.59. You may not have had the same answer as me because I led you astray and I actually forgot to transfer this 2 up here, so I had to fix that mistake. All right, and then I finished my problem. So this is the answer to our problem. The rate of change of the height of this inverted circular cone, of this inverted circular cone is 1.59 meters per second as the volume is increasing at a rate of 5 cubic meters per minute. Oh, I'm sorry, meters per minute. Now, you'll see on the answer key that's on the next slide a slightly different way of doing this problem. I can explain that to anyone if they want to know how I did this problem last year. We sort of took derivatives and multiplied them. If you've taken calculus already, you may also already know this method. But please see me at office hours if you want to know this method. Otherwise, we're going to use this particular method going forward. All right, good luck this weekend, and make sure you study for your exit ticket, which is on related rates, Delta Math style problems. Bye.